Hello there, my name is Thiago t.croisfelt.batista and I'm going to present you work that we sent to the ECOS 2020 conference. I'm going to talk about the thermodynamic analysis of the deployment of Organic Rankine Cycle in new power plants, geothermal power plants, reusing abandoned oil wells in Brazil. This work was developed at the Federal University of Santa Catarina in Brazil, and I worked here with the professor Júlio César Passos and Edson Bazzo. So this presentation is going through an introduction where I'm going to talk about the motivation and the objectives of the present work. I'm going to present you the methods that we deployed and our assumptions to simplify our models. We are going to discuss the results, and in the end we are going to summarize all the lessons learned here. It's been studied the possibility of the deployment of new geothermal power plants in abandoned oil wells. Some studies apply the concept of a single well to recover heat from the lithosphere. They deploy the double pipe heat exchange inside the well bore. The concept of the deployment of a single well in a geothermal power plant have some advantages. One of them is to improve the usage of the geothermal field area, because we no longer need a pair of wells to inject and extract water thermal fluid actually from the ground. Few research have been found related to this concept in Brazil. This may occur because we have no geothermal power plants here, even if we had about 10,000 oil and gas abandoned drillings in 2017 here. This context may highlight the opportunity to develop some kind of studies here in Brazil. So the present work aimed to evaluate the performance and capacity of the electricity generation of 4 simulated geothermal power plants in abandoned oil wells in Brazil. About the methods, we studied 4 different well bores placed in 4 different states in Brazil. They are pretty far away one from each other, so they have different climatic characteristics in the surroundings. We are going to refer to each one of these wells by the abbreviation of the state where the well is placed. The characteristics of the heat supply, so the characteristics of the hot water extracted from the wells, they got them from previous work. So we have here the water flow and also the temperature that we got this extracted water. They are results from previous simulations. The power cycle was defined to be as simple as possible. So we have the extracted water passing through an evaporator to exchange heat to the organic fluid. We deployed a concept here that the ambient conditions are constant along the year. The working fluid is R245 FA. The turbine inlet conditions were optimized for the nameplate point. We also considered the pinch point to be constant and equal to 6.4 degrees Celsius. This is a very important feature that we are going to discuss later here. So we are going to evaluate the net power output that goes out from the generator. And we are going to evaluate the overall thermal efficiency along the years of operation. We also fitted a curve for this net power output, and the integration of this curve gave to us the amount of energy produced, the estimation of the amount of energy produced in each year of the life cycle. Then, talking about the results, here we have the curves of the net power output. An important thing here to see here is that the lithosphere works as a thermal reservoir because we have a decay in the extracted energy and it trends to the steady state condition. Also, the geothermal gradient is the most important feature to evaluating new geothermal power plant project. We can see that the highest geothermal gradient here delivers the best power plant scenario. And about the curve fitting, we got pretty good coefficients of determination for this kind of regression here. So we can use this function to be integrated and to deliver the estimated the estimation of the amount of energy produced along the power plant life cycle. When analyzing the thermal efficiencies, we also can see a disturbance at the initial condition. For some wells, we have this raise in thermal efficiency up to the 5th year of operation, and for others that goes to the 1st year of operation. This occurs in different times for different power plants due to the thermal inertia of the rocks, because the placement of these wells is done in different regions of Brazil, and they have different formation of the lithosphere, different rocks, different materials, and different thermal properties of those rocks. So they have different thermal inertias. For the estimation of the energy production, this gave to us this amount of energy generated for each year of the life cycle of the simulated power plant. We can see an average decay of 34–35% over 30 years of operation. This is very important to be considered in the levelized cost of electricity. It's a parameter to evaluate the economic feasibility of the power plant. More about the economic analysis of these 4 wells is going to be published in future works. Another important thing to be analyzed here is how the energy is recovered from the hot water, how we transfer heat from the extracted hot water to the organic fluid. This occurs inside the evaporator, so here we have a division. This side we have the preheater, and here the steam generator. We have the hot water coming from the extraction, and also the organic fluid coming along the preheater here. And we can see that we do not use all the exergy that we could use from the hot water. The hot water is reinjected or is rejected of the evaporator with a high temperature here against the ambient temperature. But how could we improve this performance? How could we use this wasted exergy? We could think to change the slope of the curves to get this point here closer to the ambient condition, but we cannot do that because the slope of those curves, they depend on the properties of water and the organic fluid here, the R245FA. Also, we could try to bring this curve down, the hot water curve. We could get a condition here to get this point closer to the ambient condition, but that's not possible because we would have a heat transfer from a cold fluid here to a hotter one, and that goes against the second law of thermodynamics. This may occur in all the 4 studied cases. So, summarizing the lessons learned here, We have the technical feasibility to deploy organic Rankine cycles in abandoned oil wells. We estimated the electrical powers, the design point, the nameplate electrical powers between 10 and 14 kilowatts, and thermal efficiencies between 3 and 5%. We also have limitations associated with the pinch point, and we cannot neglect them when analyzing the thermodynamic behavior or the technical feasibility of these new projects. Also, we can see that lithosphere, the ground, works as a thermal reservoir, like a thermal capacitor. And this has to be considered in the economic analysis. We would like to leave here a special thank to the National Agency of Petroleum, Natural Gas and Biofuels of the Brazilian government, because they granted access to the data of those studied well bores. Also, we would like to thank to the coordination of the improvement of higher education personnel, also of the Brazilian government, because they funded the scholarship of the master student enrolled in this research. And thank you all for watching.